So let's get started on differential equations. So this is chapter 1. It's really just the introduction of differential equations. 1.1 is just a little bit of background. I wasn't sure if I wanted to go through all of this chapter, but I thought it might be best to do so. It's pretty quick, not a whole lot of difficult, problems and stuff. So give us a good background and basis to where we're starting. And to remind you, you've already seen differential equations before. So first, a little bit of background. And let me give you I'm just going to list some examples, okay? So here's some examples of differential equations. And of course, that's how I abbreviate. And many of these you've seen, maybe not directly, but so we'll list a few. So if I have dA dt equal to k times a, well then that can be rate of decay of a fossil or age of something. Okay, so it's a change in time with respect to time, a change of a substance with respect to time. So age of a fossil, for example. So I'm just going to write out a bunch of these examples. And there's some in the book. I pick different ones. Most of the time I will. Not every time, but most of the time I'll do something different than the book. I'm pretty much following the book section by section and picking similar things to do. Here's another one. Oh, so A would be amount. K is a constant that depends on the substance, and so but we're not going to get into those details right away. Okay, here's another one. D capital T dt equal to K times T minus T sub m. That one could be cooling of an object. So cooling of an object. Okay, here's another one. Dx dt equal to kx times n plus 1 minus x. This one could pertain to what's going on right now. This is the number of people infected with a virus. Right from the book. Now, that's probably a very simplified version of what's really going on right now, but that's the type of things you can start with. Another one, and then I'll talk a little bit about what some of the differences. So m and then d2x. So this is what we would call this a second order. I'll get more into that in a second. Dt plus capital F of x equal to g of t. That one is used for physical systems. And this is one I often choose in Calc 3. This is Laplace's equations. Partial squared u partial x squared plus partial squared u partial y squared equal to 0. And so that's Laplace. So that's what we refer to generically as Laplace's equations. And has a lot of applications. Potential theory. Electricity, heat, like equations. aerodynamics, Schrodinger equation. I'm not gonna write all those up. Uh, I found this on something I had. It's either Facebook or let me cut that actually, or Pinterest. I don't know, whatever stuff comes up. So this one I saw as I was kind of looking through the book and everything. So here's one. So check this out. Let me zoom in a little bit. This is a differential equation. This is the Schrodinger equation from cosmology. So it's the core equation for quantum mechanics. So if you're going into physics, higher up physics, you'd eventually talk about this. Well, here's Laplace's equation right here. This is basically written as like an operator, and this has, of course, the three variables x, y, z. And then so you're basically operating on the wave equation. But that in itself is a differential equation. Okay, and it's that one we refer to as a partial differential equation. So this guy here is a partial differential equation. So on all these examples except Laplace's, most of our examples really are about rate of change with respect to time of something, but it doesn't have to be. Okay, so I'll just say, just to give you an idea, so it's usually what we refer to is a rate of change. So that's what we're talking about of something. It's a rate of change of something. And it's often, I'll put a period there, with respect to time. Okay, but does not have to be. So in Calc 1 and 3, I believe, in our system, you would have seen basically a differential equation, but we didn't really call it that. So I'm going to show you an example and work it out just to kind of refresh what you've already done. So the goal, and I have this here somewhere, but let me show you an example. So this is an example, and you know what, I'm going to have to come down here. So let me just write this right here. So so just to remind you, in single variable and multiple variable, so usually, I don't think we did much in Calc 2 or 65B, but in Calc 1 and 3, we called these initial value problems. And I always make a point of focusing on this not a lot, but quite a bit in when we do Calc 3 and Calc 1 some as well, but mostly focus on Calc 3. So here's an example, and I took this right from my lecture notes. So actually, if you took me for Calc 3, you would have this in your lecture notes. What we would have been asked. So this is what it would look like. Find, again, this is just kind of warm up, reminding you of what we're trying to do. So find R of t given R prime of t equal to t e to the negative t squared I minus e to the negative tj plus k, right? So you're given R prime, you're given the derivative, and they want you to find R. But you're also given, so that R of 0 is equal to a half I minus j plus k. So that's your initial condition. Now we're not going to look at this quite this form. This is the vector valued function form, but the process and concept's really the same, that you're given the derivative or the differential and you want to work backwards to find the function. So our goal is to find the function. So if you go back, if you look at these, those all have derivatives in them, right? right? So derivative is derivative of a with respect to time, right? And this one down here is u and x, u and y. And our goal, and I'll talk more about this too, but our goal is to go backwards. Our goal is to find that original function and talk about a little theory if you can and all that kind of stuff, if it's possible. So let's work this one out. Okay, I was going to just copy it, but I figured let's just do it to remind you. Like we have been doing this already. And then in the form above, they would use a Leibniz form that's talked about in the book a little bit. Or I don't know if it's in this book actually, but drdt. I've not used this book before. drdt is the other form, and so that's the same as r prime, or if you want to put t in there, that's fine. R prime of t, and this book seems to use a lot of the Leibniz equations, or form, I should say, notation. So we'll kind of go back and forth with the prime notation and the Leibniz notation. Both are good, just depends on how you want to use it. So what we say then for this is r of t is equal to, and so you have to integrate. So we got to get warmed up on our integration skills again. R prime of t dt. And so we're going to integrate all of that. It's the integral of t e to the negative t squared I minus e to the negative t j plus k dt. All right, so maybe if you remember how to do this, work it out, because this is good, just kind of warm up, over the summer, what we would have done. So you have to integrate each one of those and then use the initial conditions given to find the arbitrary constant. So these are called initial value problems, which will be 1.2. We'll look at more of that in 1.2. All right, so if we integrate that, and I'm not going to go through all the little details like I would in Calc 1 or 2. I'll just kind of write it up. So you get negative 1/2 e to the negative t squared. Oh, and I got to say, it's really tough to be disciplined to, pause the video, work this out, go back. You got to think of it as same amount of time you'd be in class. That's what I'd have you do. I'd have you work on stuff and ask questions, but we're not there. So it takes a lot of discipline to do that and do it right. And I know because it's how difficult it is, because it's difficult for me to sit here and do this without someone there. I feel like you're doing a play, playing a basketball game or a football game or baseball game with those audiences you see right now. It's kind of absurd, but like I said, we'll do the best we can with the technology we have. Okay, sorry, I won't rant anymore. All right, so you integrate that with respect to time. So you get that. Note the arbitrary constants all the way through. And then we want to say for t equal to 0, we substitute in and then solve for those arbitrary constants. So we're going to substitute 0 for the t's here. Wait a second, let me see if I can. So for here, here, and here, and then set it equal to this, because that's t of 0. So remember, this is implied right here that t is equal to 0. So that's what we're doing. So that's what we want to do, and substitute 0 in. All right, so I'll just show you what that is. So hopefully this is very familiar, or like oh yeah, I remember doing that kind of thing. It's not too bad once you get the hang of it. It's like, oh yeah, I see how to do it. Not usually a big deal. And so this one's pretty straightforward. You just integrate the whole thing on both sides. But once we basically we're going to start building different differential equations. You're not going to have it just this one you have just r prime completely isolated on one side. So you just integrate. So that's all we really did. But we're going to develop, the whole class is about developing techniques on how to find the given function that if you put in all those derivatives, you get a true statement. We'll talk about that. All right. So that, substituting in 0, must be equal to the initial condition, which was 1/2 I minus j plus k. So here, this is more specific to Calc 3, but now equate components. And we get negative 1/2 plus C1 is equal to 1/2 if and only if C1 is equal to 1. And then we have same thing here. So 1 plus C2 is equal to negative 1 if and only if C2 is equal to negative 2. And lastly, C3 must just be 1. So where is it? Yeah, so C3 is just K, so for it to just be K, you gotta just be 1. Well, let's do it over here. So C3 is equal to 1. All right, so then that's everything, and then you would just substitute back. So therefore, R of t with that initial condition is equal to all of that, and then you just plug in the constants. So it's negative 1/2 e to the negative t squared plus 1/2 I, and then plus e to the negative t plus C2, which is, so make that a minus. So it's minus 2 j plus t and then plus 1 k. Okay, so that's old stuff. That's what we did in, I think that was chapter 13 in our book, 65, or Math 75, Thomas. So that's solving a differential equation. Now this is a vector value differential equation, but basically that's the same idea that you're doing. And so you're given prime, you want to go back and find r. You can leave it with arbitrary constants, and you get families of solutions, and that's a little bit more we'll get into. 1.3 talks about that a bit. I'm not going to get into that a lot. Talk about that when we get there. So now we want to just kind of look at some differences here. So we want to talk about what we call ODE, ordinary differential equations, versus PDE, partial differential equations. Okay, so that's the the difference. So this is called ordinary. Let's abbreviate diffie-q, or partial diffie-q. So what's the difference? It's kind of really simple, actually. Ordinary differential equations, there's one independent variable. There's no real, so ODE is one independent variable. In PDE, there are more than one independent variable. All right, so going back to the ones above, I only gave you one example where that's a PDE. So the Laplace's equation is that's a partial differential equation. Okay, and the rest of these are just with respect to time, and those are ODEs. Okay, let me give you, I have a few more examples to show you as well here. So where was I at? Okay, so here's an example. So if I have d2x dt squared plus a dx dt plus kx equal to 0 versus partial squared u over partial x squared plus partial squared u over partial y squared equal to 0. What's the giveaway between PDE and ODE? It's really the partial symbol. You can't say this as dx. You would not do that. So if you had this form and different independent variables, x and y, then you wouldn't put d. You have to put the partial. So that's really the giveaway. So that's not really tough to see whether it's an ODE or PDE. All right, so this one is ordinary differential equation, and this one is a partial differential equation. Okay, so that should be pretty clear. The goal in both cases for this whole class, really, the goal is to find x of t and or I should say, but and u of t, or whatever the variable. Oops, I didn't do that right. This would be u of x, y. Okay, so that's the goal of the class, really. I mean, that's essentially it. We have different forms of differential equations, and the goal is to work backwards using all these techniques we're going to develop to find the original function without the derivative in there. Essentially, that's it. And then, of course, we'll talk about applications. But you get more into applications as you go higher. If you're going to do applied mathematics or physics, engineering, that's where you start applying all these formulas. But you need to have all the techniques down to solve them. Kind of understand the theory and concept behind it. So in this class, we only focus on ODE. Okay, so we're only looking at ordinary differential equations in this class. Or I wouldn't say only, but that's mostly what we do. So we focus on ODE. So in other words, this class you'd call it, some schools, colleges would call this in your first ODE class, or ordinary differential equation class. Okay, so continuing, let's talk about the next thing. Let's talk about linear versus nonlinear differential equations. So linear versus nonlinear, what that looks like. All right, so first we're just going to look at the definition. I'll just define it and we'll talk about it. So here's a definition of linear. And this specifically would be linear ODE. So at some point, I'm not sure we're there yet, but at some point I'll pretty much just say, hey, we're going to only do ODEs. So I'm not going to keep having to say that. Okay, so linear ordinary differential equation has the form like this. Okay, so the form is a sub n x, and then d, and then the derivative is nth derivative of y, and then dx n. And then you just step down and we call it order, a sub n minus 1 of x, and then d n minus 1, y, dx to the n minus 1, etc., all the way down to a1x dy dx, and then your constant, so a naught x y, so it's not a derivative, and then equal to capital F of x. So note the dependent and independent variables. So here's your independent variable is your x in this form, and your dependent is your y. So there's no restrictions on this coefficient with respect to x. The restriction really is the power of your terms. Not the power, but the order of the differential, or of the terms. So you can't have basically a y in here, because it has to be just that power. It's a linear ODEs is kind of a special case, and it comes up enough to focus on it, but most of the time it's going to be different. It's going to be nonlinear. So let's look at some other examples of nonlinear. Maybe do, and then I think that's it for this section. So it's really just introducing the concept. So I got a number, and there's a good examples in the book too. Look through that. I have a few here. Let me just list out a couple here. So let's see. Yeah, so here we go. So if I have, and I'll use the prime notation to make it a little easier. I'll go back and forth. Like I mentioned, the book uses the Leibniz notation. It seems like a lot, so we don't always have to do that. But it needs to be clear what the independent variable is. That's the big difference, is you got to know what that is. Okay, so y prime cosine x y, oops, I need some making two equation, equal to e to the x, and that's in parentheses, y prime plus y squared equal to 1. Oh, so we're going to classify these. And then y double prime plus cosine x y prime equal to sine x. Next one is x y double prime plus y prime equal to x squared. Next one is x y triple prime minus e to the x y prime plus sine x y equal to 0. And I have one more, y triple prime, 1, 2, 3, minus x y prime cubed, the entire thing cubed, plus y equal to 0. So let's go through those. Let's call this an example. So first of all, we'll talk about linear or not. So I'll just say linear, and so we'll put a y or an n or no. So yes or no. So is it linear? Yes or no? And I haven't defined this yet, but what's the order? So the order is really easy. I'll do it back up here. So let's define order. Order of ODE or PDE is basically just the highest order derivative or partial derivative. So it's literally just like a polynomial. What's the degree of a polynomial? It's the highest degree term. And so that's all you got to look at. All right, so pause the video, like actually do it, and oops, and go through and tell me, list it out and see if you get the same thing. Which is it, linear or not? So you gotta look at the form, and I'll give you a little hint here. You can't have like another y term in here. The x term doesn't matter. Okay, so take a look. All right, so you did pause it, so we're going to continue. All right, so the first one was what? Is this one linear? So this is a yes. So yes, and what's the order? Order is 1, because it's that first derivative. So it's linear because you have a prime and then a y and then a function. Second one, is that linear? Answer is no. This is not linear. Because of what? It's because of this squared term here. So there's no just y squared. Right? It's not in there. And then, but the order though is 1 as well. Next one, is that one linear? Answer is no, because you have a y and a y prime right there. The cosine x and sine x doesn't matter. That's with respect to x. So is this one linear? No. And what's the order? Order is 2. And the next one, is this one linear? This one has a prime, or double prime and then prime. Yes, this one is linear. And the order is 2. Next one, is this one linear? This one looks funky, but is it? Triple prime, prime, and then just the function, just y. It's okay you're missing a term, right? Because the coefficient would just be 0. So you're missing the y double prime, but that's okay because you just have a coefficient that's 0, just like a polynomial. So this is yes as well. This is linear, and the order is 3. And this one has y prime, y, and y triple prime. But the problem is this guy right here, the cube. When you cube that, it's not the form above, right? You can't have one of these suckers up here cubed. Oops, I'll try that again. Cubed, right? It has to be just sitting by itself. And okay, so I went through this whole, so this is a no. Let me finish this before I go on to my next thought. Don't worry so much about if you're totally recognizing linear or not right now. There's some in the homework, but once you start solving them, it'll start making a bit more sense of which ones are which. Okay, I think at that point we are good. We'll go through 1.2, which is a good amount. That might take 2 videos. Okay.